You should have grabbed two things as you came in this morning. The first thing is this page, the one that's stapled together, the conduction summary. So we are now officially donezo with conduction, which is kind of sweet. But there's a lot there. There are a lot of different models, a lot of different equations. So this is my attempt at laying out a summary of the most important parts of it. So the most important part of conduction is really these top two equations. I mean, this is really what is governing all of the different models that we came up with, the heat diffusion equation. Its younger brother is Fick's law of conduction here. And these two equations combined, this is what gives us basically all of the conduction stuff that we've done. I have those two written, the gradient operator spelled out in different coordinates. In the gradient operator, and then that's the one upside down triangle, and then the Laplacian operator, which is like the double upside down triangle. So the heat diffusion equation has a double upside down triangle. The Fick's law of conduction has a one upside down triangle. So one upside down triangle is a gradient. The double is what we call a Laplacian. But basically from those, you know, if you wanted it in cylindrical coordinates, this would be what upside down triangle squared T is, just for the notation. So that lays out on the front page is just, this is the basis of all of the other stuff that we did, all of it. Then I tried to go through and say, okay, what are the different like kind of levels of models? So the simplest model that we have really, and I think the most intuitive, the one that I think is, you know, if you're walking away from heat transfer, this is something to kind of ingrain in your brain, is the thermal resistance model. Maybe not all of the details, but at least kind of the general concepts, because I think it helps you think about heat transfer problems in a way that is maybe different than if you had never seen this. Helps you get more intuition about what would happen and how much heat goes one way versus the other way, just like you have some intuition for circuits. So there are a number of different aspects to it, the thermal resistance model. Obviously, there's the thermal resistance of solids in different geometries, a plane, a cylinder, a sphere. And then also thermal resistance for convection and for radiation. The radiation one is a little bit, right? If you want to get radiation to look, we didn't really do much with this, but if you wanted to get radiation to look like a thermal resistance, it can, but it ends up depending on temperature. So if you're solving like real equations with it, it's a temperature dependent thing. But if you're looking at, say, the steady state performance of a system, you could say it could help you think through, like, what's the quote unquote resistance for convection versus what's the resistance for radiation, and give you a relatively easy way to kind of see what's the balance between these two processes. We didn't talk that much about that. Then from kind of again, building off somewhat similar things is our handling of extended surfaces. So other steady state things that we can make certain assumptions on. Then the next section is transient conduction. That's the stuff that we've been doing most recently. In transient conduction, we have really solutions for the heat diffusion equation. And we kind of have a couple different, really three different time regimes. We have something that's really fast. That would be a semi-infinite solid. We have something that's like, or something that's really fast. That's a lumped capacitance type problem. where the entire object changes at one constant temperature and the whole object heats up or the whole object cools down. We have a way to check that called the BO number. Then we have a semi-infinite solid where it's like just the surface of the object is heating up and cooling down. And then kind of in the middle, what we call our exact solution, where we're going to have temperature differences between the middle and the surface, but the whole object is still heating up and cooling down, but we have temperature differences inside of the object. So we have a couple different ways to then kind of handle that depending on which time regime we are living in, and at least for the lumped capacitance model, what our boundary conditions are. For the other two, for the semi-infinite solid model, what our boundary conditions are. For the exact solution, we only have one set of boundary conditions that we can really solve, that we've solved. So we haven't solved for any other, any different boundary conditions. Like we just have convection at the surface, and that's what we used. Then the last thing to note is the stuff that we've done most recently with 2D conduction, where we've looked at some basic numerical methods. And really the kind of take home from that is once you get the hang of it, it's really easy because you just look at a temperature and you say, that's going to be the average of the temperatures around it. Okay, well, how do I calculate the average? Well, I add up the temperatures times a weighting factor, where that weight is like, what's the dimension of the side that those objects share? Or if it's a surface, that dimension of the side times the BO number if it's a surface experiencing convection, because you have to weight it by what does convection look like on the surface. So a lot of stuff there. I tried to leave enough space there so that this can kind of turn into, say, a note sheet for the upcoming exam or final exam and or. Upcoming, I mean that in a very general sense. It's not coming soon. The one thing that is coming relatively soon, as in like Thursday, is a quiz. So there's going to be a quiz. It will be one problem. It will be a time-dependent heat transfer problem. So we're going to be living in this section. And it's going to be a question that's going to ask you to do something. So you're going to have to identify which model do I need to use and then answer the question. So it won't be prescribed like use the lumped capacitance model, use the exact solution model, the semi-infinite stuff. You have to figure out what's an appropriate model to use and then use that model to calculate the number. I'm anticipating it will be a little bit longer quiz, but it's not going to be super crazy. I'm kind of anticipating it maybe being like a half hour though total, but I'm attempting to design the question so that I think it's like a 20-minute question-ish. But that's coming on Thursday. So I'll release, I haven't yet, the solutions to the not this homework assignment, but the last one, so that you guys have that if you want to look over some of that. But I mean, a lot of the information is kind of once you have the model that you're going to use, it's like plug and chug a little bit. So I don't think a lot of the strategy is how do I take these models and answer questions? How do I plug and chug correctly? But also how do I identify where I am, kind of what regime this process sits under. So that's going to be coming Thursday. I think we'll just do that I'm kind of thinking we'll do that at the end of class because it's going to be a little bit longer quiz, so that then when you're done, you're not waiting around. You can pack up and leave.
Are we going to get like a sheet for that?
So the question was, are we going to get like a note sheet for that? So I'm thinking, and I'm willing to discuss this. I'm thinking of like just kind of as practice, you can use this and mark it up and write notes on it. And then that will be able to transfer over to the final exam or exam 2. Really both of those places potentially. So that was my plan. Does that sound like, do you feel like you would want other notes than that? I mean, okay. Okay. Yeah, so that was my plan, is that you'd get this. You may write on it. So handwritten notes on this are fine. I encourage it very strongly. For sure, go through this section at this point, because it's not going to be anything else. So go through this, what is it, section 3, section 4, where I cover all of the transient conduction stuff. Go through that, right? And you're looking to add, like, the equations are already there, so you just need to add the context to it. Like, what do I look at to make sure this model works? What am I looking for to make sure this model is working? What does the system look like for, like a little diagram or something like that. So, like, what is L and what is, what is 0 and what is 1, things like that. Where's the surface? Where's the center given this specific model? Because they're not all the same, right? So 0 for the exact solution is in the middle of the object. For the semi-infinite solid, 0 is at the surface. So just like little pictures to help you make sure you know how to actually use these equations. So that's coming, but the good news is we're wrapping up conduction. The reason we spent so much time on conduction, right? It's now week 10, which feels a little crazy. But the reason we spend so much time on conduction is a lot of the, like I said, this class is a lot about kind of engineering problem solving. And I think conduction provides a relatively easy way to look at how we apply differential equations to real world systems, how we can take models and build simplifications that help us gain intuition for how systems behave and respond. And also because, as we'll see, convection, which we're going to move to next, requires that you do some of those same things, but kind of at a higher level. And also that you understand conduction, because convection, as we'll see, is really just a specialized version of conduction with some extra stuff going on too. So we're going to switch over. I'll finish talking about conduction because I think we've spent a lot of time on it. But we're going to switch over to talking about convection. We'll do that by flipping to the other sheet that you guys have that you picked up in class number 7. And to be able to look at in class number 7, I guess just one quick comment. You don't need to write this down necessarily. But right, so far, what we've looked at is obviously, like, we have our conduction model. For our convection model equals HC T minus T infinity. We have this model. Our whole goal is going to be, in what we're doing, to find that. So we're going to use different strategies to approximate and estimate that, to be able to understand what are the factors that make it bigger or smaller or change along a surface. What are all these different things, so that we can get good estimates of that and really build an intuition, like what are the things that matter for convection, rather than just, right, so far I've either made up a number and given it to you. Sometimes I haven't made it up, sometimes I've calculated it, but most of the time I haven't. Most of the time, maybe it's just a number I threw out. Or it's something that you guys kind of made up by looking at, is it table 1.1? So how do we build back in like some actual engineering instead of just making things up? In order to do that, we have to understand a little bit how fluids actually behave. So convection is something that's obviously going to happen at the surface of an object. So we have to understand something about fluid behavior at the surface of an object. So if you've taken fluids, this is going to be stuff that you've seen before. It may not be stuff that you remember, but you've at least seen it. If you're in fluids right now, you'll see some of this same stuff come up fairly shortly. I guess in a couple weeks. You'll probably even watch parts of this same video. But what we're going to do is watch this video. We'll watch about what is it? We'll watch about 10-ish minutes, 10, 12 minutes of the video. And it just kind of goes over, I think it has some good visualization for what's happening at the surface of objects. It attacks it from a fluids perspective instead of a heat transfer perspective. But I think that's okay because you have to, like, the reality is we have to do both. We have to understand the heat transfer part, but we also have to understand the fluids part. So we'll be looking at kind of the connection between these two aspects of it over the next while. As the video is playing, you should be, let me see. I'm going to try to play it on the other computer so that I can put it through the speakers because I want you guys to hear it. So let me pull it up on the other computer and switch computers. Yeah. All right, give me a second, everybody. You can tell I apparently didn't rehearse this well enough. Okay. All right, so we'll try. Okay.
This drawing, derived from potential flow theory, shows how the streamline around the combination of a flat plate and a cylinder would look if fluids did not have viscosity.
So I'm going to pause it and talk a lot because I'm sorry. So what we're looking at here, we're going to be looking at is a flow from left to right. For a refresher for those not in fluids or not thinking about this for a while, right? Those little lines that we're going to be seeing are actually going to be, this is water flowing. The little lines that we're going to be seeing are bubbles of hydrogen to help us visualize what's happening. This is just a drawing of what it quote unquote should look like if viscosity in fluids was not a thing. So this is kind of more of a fluids appropriate thing, but you can see a little bit how the real system changes.
Water flows around the same shape as flow with a pipe system. Boundary layers, thin layers of fluid in which viscosity affects the flow dynamics, are formed along the surfaces of the object. The behavior of these boundary layers under the influence of pressure gradients can, in some cases, drastically alter the flow. This streamline pattern is very nearly what one would predict from an viscous flow theory. Because the Reynolds number is large, influences of viscosity are confined to a narrow region close to the surface of the wing. The primary effect of viscosity is simply to create a drag force on the wing through the integrated effect of surface shear stress. As the angle of attack is increased, viscous effects become more pronounced. Pressure gradients imposed on the boundary layers become more severe, and separation occurs on the upper surface. Now the airfoil is full. A region of recirculating flow is formed over the upper surface of the wing. In order to understand how viscous forces can influence the entire flow field, we shall look at what causes boundary layers, how they grow, how they respond to pressure gradient, and the difference in behavior of laminar and turbulent layers. Before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone.
And this is really where
Of water flowing in the cell are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timeline, the vertical patches of bubbles, remaining perpendicular to the streamline, shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the steering forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected.
Okay, one, I just want to point out that this is all like, there's no movie magic here. This is just like filmed of like above an experiment, which is kind of wild. So what you see there, this is the part that I want you to kind of key in on. So you see there's an area where basically the flow is unaffected. And there's this area by the surface where we're starting to get some effects of basically like, you can think of it, he talks about vorticity. Don't worry too much about that word. We're not going to talk about it here ever. But essentially what you can think of is, okay, all of a sudden at this thin layer, which we call the boundary layer, we like quote unquote start feeling the surface, right? That's the layer where things are actually close enough to the surface that you feel it. In this case, we feel it, we feel the surface because of viscosity. So our velocity is changing, like we're slowing down close to the surface. And we do that because at the surface itself, we experience what we call the no-slip condition. So the surface itself, you can kind of see it visually right here. You can see some bubbles that touched the tip and they got stuck there because their velocity is going to go to zero when they're at the surface. So those bubbles get stuck at that tip. But basically, what we're going to see is that surface is obviously what's causing changes in velocity above it. And we're going to look a little bit at some of the math and how that changes as we move down a surface and what that looks like.
The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free-stream velocity will give a better view of the boundary layer growth. The velocity throughout the boundary layer is less than that in the previous screen. There is no split between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-split boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer.
So we're going to draw, I think question 1 asks you to draw things that look sort of like this. But we're going to draw boundary layers a little bit like this. So to show, this is showing the velocity profile. So it's showing the velocity everywhere. And what he's saying is basically if we make one of these like lines of bubbles, it's essentially going to be a visual representation of the velocity profile, right? Because if you turn on, what they do is turn on a voltage along a wire, and that blows bubbles because it electrolyzes water into hydrogen. So they turn on a voltage to this wire, it forms bubbles, and then how the distance that those bubbles move over a given time is just the velocity. So he's going to do basically an experiment that will give you a visual representation of exactly the velocity profile along this surface.
Here's of the boundary layer, and sometimes defined as the Wilson delta from the surface to where the velocity u reaches some fixed percentage of the previously value. For our purpose, we will use 95% of the previously velocity to define the thickness of our boundary layer. The gradient of the velocity normal to the wall, delta u by delta y, times the viscosity in u is the wall's infiltration or shear stress cutoff. The greater the velocity gradient normal to the wall, the greater the shear stress. The wall, delta.
Okay, so for number one, you should be able to answer number one. For number two, you're going to draw two pictures that look like this. One that is upstream and one that's downstream along the plate. So we'll look a little bit, I think right after this, he shows exactly what that looks like.
By delta y, times the viscosity in u is the wall's infiltration or shear stress cutoff. The greater the velocity gradient normal to the wall, the greater the shear stress. Upstream, the velocity gradient is very high. Downstream, it is much less. This composite photograph compares the two velocity profiles. The smaller gradient downstream indicates the wall shear stress decreases along the plate. The growth of the boundary layer thickness along the plate can be explained by considering the time history of the vorticity within the boundary layer.
Yeah, he just used big words. Don't be scared. You guys know big words too.
Theorem states that the area integral of the vorticity omega, bounded by a closed contour, is equal to the line integral of the velocity around the bounding contour.
That was clear to everybody, right? Okay. Don't worry, again, don't worry about the word vorticity or what he's talking about there. Hopefully you guys have a chance to have drawn number two. So while he's talking about this, finish number two. And then he'll move right to number three.
The circulation gamma is the sum of the vorticity enclosed by the contour. The contour at the upstream station is a unit length along the plate and is more than a boundary layer thickness in height. At the top, the local velocity is parallel to the contour, but in the opposite sense. The components of velocity along the right and left parts of the contour are virtually zero. Because there is no slip, the velocity contribution to the circulation at the surface is in fact zero. Therefore, the circulation is minus the free stream velocity times a unit length. Downstream, the circulation is also equal to minus u naught times the unit length. The total amount of vorticity within each contour is the same. Because there is no vorticity upstream of the plate, and because the circulation per unit length along it is constant, we conclude that all of the vorticity is length. Upstream, 95% of the total vorticity is contained within this area. Downstream, 95% of the total vorticity is contained within this area. Viscosity acts through the mechanism of molecular diffusion to spread out the vorticity as it is convected downstream.
Okay, so what he said there was maybe confused by the language that he used because it's different than maybe language that you've heard before. Basically this gradient in velocity ends up getting smeared out because of the diffusion of momentum. So that's the mechanism that causes this boundary layer to grow. Hopefully that's part one. So momentum is diffusing from kind of this momentum change at the surface where all of a sudden we come to from some velocity to a stop. That ends up diffusing up in the same way that heat diffuses by conduction. It diffuses up through the system because of the viscosity. So he'll go through and right in a second here give you an answer for 3, but it'll be fairly clear. There'll be an equation and kind of go through and derive the answer to number 3. So just look at number 3 so you know what it's asking, and then get ready for an answer here fairly shortly.
Vorticity has the duration of height. We can relate the factors of controlling the growth process in the following simplified manner. The diffusion rate delta increases as the square root of the product of the kinematic viscosity and the time of diffusion increases. As using L in the leading edge, the diffusion time is proportional to L divided by free stream velocity U0. We combine.
Right, just to pause it here so that we can see all of the different variables. So there's a time component to it, which is related to how long it took you to get a certain distance. So that's where the time comes in, like how long did it take you to travel, for the free stream to travel this distance, L. So L over U infinity, or U naught, that's the free stream velocity. This little V term called nu, that's the kinematic viscosity. So for those of you in fluids, or those of you who haven't taken fluids for a while, it's not mu, that's not the dynamic viscosity, that's mu divided by rho. So the viscosity divided by the density. The viscosity divided by the density, this kinematic viscosity, that's what governs how quickly a momentum change at the surface, like the surface coming to a stop, the kinematic viscosity dictates how fast that happening, like that change kind of propagates up into the fluid above it. So that's the kinematic viscosity divided by density. You can think about it a little bit just like, okay, what would happen? So for that momentum change, like the stop at the surface, for that to propagate up through the fluid, there's going to be something related to like the viscosity. How much friction is there between the different layers of fluid? So how much friction forces are kind of like pulling on the layers above it? That's the mu part. Density is like how much inertia does the fluid that's traveling have? So those two things are related. That's why we come up with this. Like what really governs it is this ratio of viscosity divided by density, or nu, the kinematic viscosity.
So delta over L is proportional to 1 over the square root of the Reynolds number. This relationship is about only a high Reynolds number, when delta is small compared to L. Increasing the flow velocity will decrease the boundary layer thickness at an inferior integration along the plate. To see this effect, here is the normal flow. We will speed up the flow. Now, the flow velocity outside the boundary layer is increased. At any position along the plate, the boundary layer thickness is now less than before, because with a higher mainstream velocity, the boundary layer has had less time to grow. We have seen details here of three-dimensional boundary layer on a flat plate in a uniform velocity field. So far, the pressure gradient in the flow direction.
Okay, and we're going to stop it there. Okay, so you should have all hopefully gotten 1, 2, and 3. Right, so the boundary layer growth is a function of what we call the Reynolds number. Hopefully you got that. For those of you that are just in fluids, we just introduced the Reynolds number. So hopefully that looks a little familiar. For those of you that took it a while ago, hopefully you remember your old friend, the Reynolds number. If you flip the page over to question 4 asks you to take that, and we're going to start to transition a little bit from thinking about this in fluids and velocities to thinking about this in heat transfer and temperature gradients. There are going to be a lot of analogies between the two, but just spend in part 4, you know what the Reynolds number is. It's the velocity. I've called it U infinity. That's the term that we'll use for this free stream velocity, like the velocity far away from everything at infinity. L divided by, L is like the distance along your plate, divided by nu, viscosity divided by density. We're going to relate these by what we call the Prandtl number. You guys are, which is a ratio of the kinematic viscosity nu and alpha, which is the thermal diffusivity. So it's going to be, or it's a ratio between how velocity changes are going to be propagating. That's the kinematic viscosity, right? How some change in one location, how that propagates up because of viscosity. And alpha, which we know from heat transfer, is how does temperature move through something. So just spend a little bit and try to math your way from the equation that you got for 3 to a new equation that talks about how would a temperature boundary layer grow as we go along a surface like this. So just spend a few minutes doing that while I shift over from one computer to another and get us set up to hopefully go over some of that stuff. Okay.
Right.
Do we feel like we're on the right track? Not at all. Shake heads, yes or no. Not on the right track. Lots of no's. Perfect. This is why we do this. Right. So what I'm asking in question 4 is we're going to be, well, let's get out notes for a second and then come back to question 4. So put away question 4. Let's get out a page and we can take some notes together. Okay, let me erase this. I'll write it back up in a second. Okay. All right, so in order to find H, we're going to be asking ourselves what's actually happening in this layer where changes are taking place in this boundary layer. So let's consider the fluids problem first that we just saw and see how it connects to the heat transfer problem. So we'll look first at flow. Right. In order to do this, in order to build our intuition, we're going to start as simple as we can. So we're going to start flow over a flat plate, just like we looked at, and it's going to be isothermal. Okay, so that's the system that we're going to be thinking about. Flow over a flat isothermal plate. So constant, it's just a plane, and it's constant temperature everywhere. So if we look at, to just draw like a schematic of what we just looked at, here's our plate. Out here we have a velocity. We'll call this U infinity. So that's like one of these solid vertical lines that we just saw. So that's going to be flowing at a known velocity, what we call the free stream velocity. Once it gets to the plate, right, it's going to be something like this. So it will still far away have the same velocity, but right at the surface it was slowed down, just like we saw. A little bit further yet, now that like slowed down part, that momentum change, the velocity change, has started to propagate up into the fluid by diffusion of momentum would be the correct term. So basically that momentum change has started to propagate slowly up by what essentially is a diffusion process. So that looks, right, essentially we're the same velocity far away, but we start to see something like that. So as we go along our plate here, the thickness of the boundary layer, delta, I'll write it like this, delta of x, because this thickness here, that's delta. That's the thickness of this velocity boundary layer. It's the thickness where we actually see like there's some velocity differences there. That's, and again, the thickness where we like quote unquote feel the fact that there's a surface there. Above that, it has no idea that there's a surface there, but in that region, that's where we feel the surface. So U, just to define some terms, is the free stream. velocity. So this is the boundary layer. Is characterized by velocity gradients and shear stress. And this happens because of the momentum diffusivity nu. Again, just as a reminder for fluids folks and for those who have taken it maybe a while ago, the shear stress, we could write tau equals mu du dy. So viscosity times the gradient of the velocity. So times the slope. We can also, this maybe feels a little bit weird, but we can characterize the boundary condition in this case as, right, like the boundary condition US equals 0, the no slip condition. The velocity at the surface is equal to 0. Okay, now let's look at what similar things we should see in flow over an isothermal plate. What should we see in the temperature or what's happening in temperature? So how did I write that? Okay. So we're going to try to draw the same picture and see where the analogies are. So we have the same flat plate. We're going to have flow over that flat plate. That flow, the fluids over here, the same picture, except now instead of velocity, what we're thinking about is temperature. So we'll call this T infinity, where the size of those arrows, that's the magnitude of the temperature. So say those arrows are like 100 degrees long or 20 degrees long, whatever it is. So the length of it, as they get bigger, you get hotter. As you get shorter, that gets colder. So this fluid is also traveling at some velocity. So there's also a free stream velocity. It does matter. I'm just not kind of showing it pictorially here on this image. Our surface, this is an isothermal plate. So our surface, TS equals, I don't know, I guess TS. Right? That's going to be our boundary condition. The temperature, we defined this as an isothermal plate. So the temperature of the surface of that plate is some number. I don't know what it is. Let's say that it's hotter than the fluid. Okay, so it's some hot temperature. So we have this hot plate and a cold fluid. The fluid's flowing over it. So what's going to happen is heat is going to be moving up into the fluid. But basically, as soon as we come into contact with the plate, the fluid that's like the surface, it's kind of an analogous to the no slip condition. That fluid at the surface is very quickly going to reach the temperature of the plate. So if we look right here at the beginning, we have far away, we haven't felt the plate yet, but right here at the beginning, we're going to be at TS right at the surface. So we can draw our arrows, but obviously out here we're still at T infinity. And as we move down along that plate, heat's going to be continually flowing from the plate up into the fluid. We're going to be continually pushing heat up. So what's going to happen is that temperature is going to kind of grow. The temperature boundary layer, the thermal boundary layer, is going to grow as we move along the plate. So if we look somewhere down here, we would expect to see, again, at T infinity, or at far away from the plate, we still haven't felt it. But maybe we look something like so that's still TS. This is still T infinity. And we look something like that. And we could draw, just like we did for the last one, we can draw the thickness of the boundary layer as we progress along the plate. Let me draw it a little bit better. So we're going to differentiate between the thermal boundary layer and the velocity boundary layer. The velocity boundary layer is delta. The thermal boundary layer is delta sub T for thermal, for temperature. The thermal boundary layer is defined by, or characterized by, by temp gradients and heat transfer. The challenging part about this is, so both boundary layers form simultaneously. I don't think I spelled that right, but close. You can spell it right, hopefully, in your notes, or spell it wrong like me. I don't know. Did I get it right? Form. I didn't spell form right. Good catch. Did I? So simultaneously, but not form. That's how I go. So both boundary layers are forming simultaneously, and delta is not necessarily equal to delta T. So, right, the boundary layers are different. And they're different because different mechanisms are creating them. For the temperature boundary layer, heat transfer and temperature differences, those are the things that are creating that thermal boundary layer. For the velocity boundary layer, momentum and diffusion of momentum, viscosity, velocity gradients, those are the things that are creating that thermal boundary layer. So the challenge of convection is that you have both of these things happening at once. Problem 4 on the in-class thing is asking us to connect. Can we connect more directly what's happening with the velocity boundary layer to how things would be happening with the thermal boundary layer? So the velocity boundary layer, what we said is this thickness, delta, is proportional to the square root of the kinematic viscosity times time. Right, that's how it grows. It grows as the square root of the kinematic viscosity times time. So the kinematic viscosity being the how fast momentum changes diffuse through a fluid. For the temperature boundary layer, we're going to say something exactly analogous, but how does temperature move through something? It moves by conduction. So for the temperature boundary layer, this guy grows proportional to the square root of alpha times time. And I understand this is proportional. This is alpha. I understand those are hard to differentiate. We need like a new alphabet, like in addition to Greek. Maybe we can use, I don't know, like Arabic numbers and stuff, and letters as well. I don't know. I feel like we need more variables. Anyway, so proportional to alpha, which is the thermal diffusivity, how does heat diffuse through an object? The velocity boundary layer is going to grow proportional to the momentum diffusivity. How does momentum change? Or velocity, how does velocity diffuse through a fluid? So these two things are going to be very analogous, but obviously nu is different than alpha. But we have what's called the Prandtl number, which is the ratio of those two things. So if you can go back to number 4 on the in-class, see if you can spend a little bit of time just trying to relate really from these two equations, how the boundary layers are going to grow. And you should end up with a similar equation like you ended with part 3, that was like, it's a function of the Reynolds number. For part 4, it's gonna be, okay, Reynolds number is gonna be part of it, but also Prandtl. So these are, those two guys are equivalent, but
Yeah.
you can use that. You really don't. Yeah, so what is time component is how long you're giving the boundary layer to grow. So it's related to velocity and distance down the. Flip it over to 3.
Oh, yeah.
Yeah, you know.
So time is L over U. So plug in for T. Plug in L over U into G. So that, what you just did, that's what we did on. Right, so to go back. Yeah. So you plugged in new T, and then for time, the time is what, how far did you move down the plane? So that was the distance down the plane divided by the velocity. So you just plug in L over U for T, and then that's going to be applied for U. So here you plug in for T.
Yeah.
You plug in L over U.
So the 791 over.
And then you, so the Reynolds number is U L over V. So U L over V would be the Reynolds number. The Prandtl number is V over L. So you're going to use, like, there's going to be underneath that square root, there's going to be some combination of Reynolds and Prandtl. Okay. We're making progress. Not so much. Medium progress.
We've been just began really discussing. Okay.
So that means I was still getting.
Well, because a bit further.
So what's the,
I mean, essentially, we're just trying to get a better understanding.
you're right?
No.
So the, we'll get over the. Oh, well, you have to. Yeah. So in 3, you wrote, this is how the number is. So, for example, time is like how long you're going to it. So it's a lot, length divided by a lot, like how long down. Divided by how fast going. So for here, the boundary length by alpha is alpha.
Okay, I guess I could that one.
So time is limited to the same time. Length over time.
Great, you agree.
Oh,
You ended up with them?
What do you get? I got L over, but now we.
Yeah.
That's neat.
You're cool.
You're not totally, like, the way you're trying to do it is.
Yeah.
Okay, so I want to make sure we have a chance to all actually get the right answer for this one.
That helps with. Because of all that else.
Not fluid. Okay. So, just so that I don't want you to be on a different page with this, because I think it is important to actually get the right answer. So for part 3, we're looking at how the velocity boundary layer is growing. I don't know why it does this to me all the time. We're apparently going to do this in red. So the velocity boundary is growing proportional to the square root of nu t. Our time is how long we give it to grow. That is equal to length over what they call u naught. What we will typically call in this class u infinity, but I guess you can keep it u naught, the free stream velocity. We basically took this and plugged it in right there. Then we can say that, okay, so delta is proportional to the square root of nu L over u. So then we do a little bit of kind of weirdness. So this, right, the square root of nu L over u is equal to L. So we can kind of pull out an L squared over nu, right? Do we get the algebra that just happened? So let me do all the steps. So this is equal to L squared over L, which is equal to L times the square root of nu u naught L. Right, does it help to see all those steps? Yeah, Nolan.
Little L, same thing as big L. The next page of rounds into one thing the
Length down plate. So the Reynolds number is going to be increasing. Like the Reynolds number is going to be changing. So every specific point down a plate is going to have its own Reynolds number based on like how far down the plate are we right then. And we'll talk, as we do this, we'll talk more about this. But Reynolds number at X equals again, to put it in kind of our notation, u infinity times X divided by nu. So we'll use this and we'll write it again in our notes and I'll explain it again. But the Reynolds number at any given location is equal to like how far we traveled down the plate in that specific instance. Okay, so let's jump. So we have a couple minutes. Let's jump to the thermal boundary layer. The thermal boundary layer. So delta T is proportional to alpha times time. Again, this is the first one is the proportionality constant. The second one is alpha. So I'm going to do a substitution. So Prandtl equals nu over alpha. Try to make that a little bit more angly. So alpha equals nu times Prandtl. Right? We agree that we can algebra that. Sorry, nu over Prandtl. Is that right? I can't algebra that. Okay, so what I'm going to do is take this now and plug that in there. So our thermal boundary layer was the square root of nu T over Prandtl. That's all underneath the square root. And then I can kind of do the same things that I did in the step before. So T equals L divided by U infinity. So I can plug that in there. So delta T equals L over, sorry, nu L over Prandtl struggling with my writing, over U infinity. Sorry, these shouldn't be equals. These should be proportionalities. So delta is proportional to nu L squared over Prandtl U infinity L. And then I can pop the L out. So delta is proportional to L times the square root of, now this is going to be 1 divided by Prandtl times the Reynolds. And the take-home message is the analogous nature of these two systems. We can just look at the ratio. The Prandtl number is the ratio of how momentum diffuses through a system versus how heat diffuses through a system. And the way that the boundary layer grows is going to be analogous in both things. It's just, okay, now we have to add in the ratio of these two similar but different physical processes: momentum diffusing through a system and heat diffusing through a system. So we will stop there because it's 9:20. We'll pick up with all this stuff on next time. We also will have a quiz next time. So there's some info on the quiz online on Moodle. You'll also see some of this stuff, but hopefully this helps at least make sure we get all the algebra parts correct.